Now, every day when you come to lecture, when you understand something, all right, when you go home, prepare your note, prepare your one-page note, every day, okay? By the end of the week, use your one-page note to answer the quiz questions, homework questions, and then discussion worksheet questions. If you can answer those questions, you're fine. You're done. You don't do anything else. No exercise, something like that. Okay. But if you find that you cannot still answer some of the questions, all right, then you come to my office hours and then talk to people, and then once you figure out how to do that, write that on your one-page note. Okay, you fix the one-page note. All right. By the time the exam rolls around, if you keep doing that every week, those little things every week, all right, you will have a perfect one-page note. And when you go to the exam, guess what? You won't even need the one-page note because you already know what's going on there. All right, that's the way to do it. This is the way. All right. Okay. Now, before I look at your answers, okay, let's see what's going on here. Now, image 1, what do we have in image 1? What is image 1? What is it? Anybody? What is image 1? Thank you. What is that, sir? Thank you. It's an infrared image or a thermal image. All right. So what radiation do we use there? Of course, infrared radiation. Right? That's IR. What about the second picture? What is it? Is it an embed? What radiation do we use there? Yeah, we use UV. Thank you. What about the third image? What do we have there? Yeah, it's an X-ray image, right? What radiation do we use for X-ray imaging? Thank you. X-rays. Thank you. Right? Yeah, we use X-rays for X-ray imaging. Okay. Now, the question is the wavelengths of this, because wavelengths are related to the energy of this radiation. Okay. And then out of these three radiation, which radiation has the highest energy? IR, UV, or X-ray? Yeah, X-ray has the highest energy, right? X-ray has the highest energy. If it has the highest energy, what can you tell me about its wavelength, relative wavelength? Should it be the longest or shortest? Or shortest? Those are the options, right? Okay, one more time. If it has the highest energy, its wavelength must be the shortest. Okay, shortest. All right. So that's the relationship tested here. Okay. So because, how do you know that? We know this equation, energy of a photon is given by hc over lambda, or wavelength. Okay. Energy and the wavelength are inversely proportional to each other. Shorter the wavelength, higher the energy. Okay. So in other words, the shortest wavelength we have in B, therefore X-rays must be B. Okay. And then out of these radiation, IR and UV, which one has a longer wavelength, IR or UV? Which one has a longer wavelength, IR or UV radiation? IR, okay. Okay, so therefore IR must be 1, right? That leaves UV to go with A over here, right? So I'm going to look at your answers and see whether we need to do something, recap what we have discussed already. Give me a second. Here are your answers. All right. So B is fine, but we need to, we can do better on the other ones a little bit more. Anyway, so just to make sure everybody's on the same page one more time, let me go to the electromagnetic spectrum. Okay. Only two colors I asked you to remember was the red and violet, right? So red is over here with 700 nanometer radiation, and then and violet is over here. Okay. Below red, when I say below red, I'm meaning energy-wise. Below red, we have what? Anybody? What do we have below red? Infrared. Infra means below, right? Below red, we have infrared, meaning it has a lesser energy, lower energy than red light. Okay. So here we have infrared radiation going from 700 nanometers to 1 millimeter till about 1 millimeter wavelength. Okay, longer wavelength than red light, we have infrared radiation. And then when it comes to microwave goes from 1 millimeter to about 10 centimeters. Right, it's going to be microwave. I'm going to use mu wave to indicate microwave. Okay. And then we don't care about the radio wave. I mean, we have it longer than that because we only go from microwave to UV, I mean, in our class. Anyway, when it comes to the other side, we have beyond violet. What do we have beyond violet? Ultraviolet. And ultraviolet has radiation with the wavelength lower than 400 nanometers. Okay. So in this region, we have ultraviolet radiation. Okay, they have wavelengths lower than 400 nanometers. And then we have X-rays and gamma rays. But in our class, we will stick with between microwave and ultraviolet radiation. That's it. All right. Do we have any questions, concerns, comments at the moment? Anything? Okay. And then in this diagram or in this electromagnetic spectrum, please note that the wavelength increases in this direction. Lambda increases in this direction. Okay. And then the energy increases in the other direction. Okay. So higher the energy, shorter the wavelength, in other words. All right. Do we have any questions, concerns, comments, Lucy? Ultraviolet is below 400, the wavelength wise, it's going to be shorter than 400 nanometers. Any other questions, concerns, comments at the moment? Anything? All right. So with that, what we're going to do is, okay, so together with the electromagnetic spectrum, okay, please keep this equation handy. Energy of a photon is given by hc over lambda. All right, this shows you the relationship between the wavelength and the energy here. Okay, they go hand in hand. All right, now let me clear my doodling. What I want to do next is I want to talk about the interactions between the light and matter. Okay, all this time we just talked about the properties of light. We talked about the wave nature of light, and we derived the relationship between the frequency and the wavelength, which are inversely proportional to each other. And then we talked about the particle nature of light. We defined the energy of a particle. Okay, energy of a particle is proportional, directly proportional to its frequency, or inversely proportional to its wavelength. All right, and then we got the equation: energy of a photon is equal to hc over lambda, or Planck's constant times the speed of light divided by the wavelength. It's giving you the energy of a photon. Okay, now those are the properties of light. Now, for our purpose, we are trying to determine the structure of the particle. To do that, we need to talk about or understand the interactions between the light and matter. Okay, so interactions between the light and matter can be in different flavors, like it can be I don't know, reflection, refraction, diffraction, or like many forms like that. But when it comes to light matter interactions, for our case, we will be focusing on light absorption and light emission by matter to understand understand the structure of the particle. Okay, so the study of light matter interactions in the flavors of absorption and emission is known as, anybody who read the textbook, what do we call this? We call this spectroscopy. Okay, the study of light matter interactions in the forms of absorption and emission is called spectroscopy, and that's what we'll be doing today. Okay, talking about spectroscopy and how to explain it. All right. And then, as I understand, you guys have started talking about absorption spectroscopy in the lab. Is that right? Yeah. Okay. Yeah. So should be relevant now. All right. Now, there are two things I want to mention before I dive into this. I need to do something. Give me a second. I'm gonna get back to my slideshow, but before that, in my notes, I want to draw two things. Okay. I'm okay. All right. So when it comes to absorption spectroscopy, okay, let's talk about absorption spectroscopy. Okay, so absorption spectra can be presented to you in two modes. Okay, I think the first mode you are familiar with, all right? In the spectrum, what do we have in the y-axis? Anybody in your lab? In the y-axis, you had absorbance, is that right? Okay, we had absorbance in the y-axis. And what about the x-axis? What do we have in the x-axis? The wave, or lambda, or the wavelength, right? Okay. And then based on what wavelengths are absorbed by your sample, you're going to see peaks in the spectrum like that. Okay, I think this is kind of you're used to. This is the most common method for mode for absorption spectroscopy. But there's another mode that we use in absorption spectroscopy. In that case, our y-axis, our x-axis is the same, still the wavelength. Okay, but here we have transmittance in the y-axis instead of absorbance. Okay, the idea is this: if your sample does not absorb any light, okay, you won't see any change in transmittance. You will see 100% of light transmitted through your sample. Okay, all the light you shine at it will be transmitted through your sample. Okay, that's called 100% transmittance. But if your sample absorbs light, okay, what is going to happen is your transmittance is going to dip. For example, if you have a peak over here, then you will have a dip in the transmittance, meaning that wavelength is absorbed. Let's call it lambda 1, same here. Okay, it's absorbed by your sample, right? And then you have another peak around here. Okay, lambda 2. See lambda 2 like here. Okay, you will see that you have dips in the transmittance when your sample absorbs light. Okay, so that's like upside down absorbance spectrum. In transmittance mode, you get the upside down peaks, meaning you have dips in the transmittance when your sample absorbs light at that particular wavelength. All right, do we have any questions, concerns, comments about that? Any questions, concerns, comments? I want to talk about this because when it comes to IR spectroscopy, which is one of the main spectroscopy technique we are going to be using in this class, they almost always use the transmittance mode. It's not the technique or not the mode you're using in the lab. Okay, I just want to point out the difference between the absorbance and the transmittance. All right, just for the completion of our notes, I want to mention about emission as well. Right, and when it comes to emission spectroscopy, okay, it's more straightforward. We would usually have intensity on the y-axis, and then the wavelength, okay, or lambda on the x-axis, and then we will see peaks depending on what light is being absorbed, like that. Okay, and sometimes the emission spectra are given as a band as well. Okay, if you don't think about the intensity that much, okay, so what we can do is we can say that this is still the wavelength, right? Wavelength. Okay, this is the wavelength. Let me just make sure I write that. Because some might get confused here, but anyway, this is the wavelength still, right? Sometimes you will be presented a band for emission spectroscopy rather than a spectrum. Okay, so you will see like a band over here, here, or here, depending on what wavelengths are emitted. Okay, for example, if this is lambda 1, lambda 2, lambda 3, and lambda 4, instead of having like intensity on the y-axis, you can say this is still lambda 1, lambda 2, lambda 3, and lambda 4. Okay, that's the other way you can be presented emission spectra. All right. What questions, concerns, comments do we have at the moment? Anything? Any questions, concerns, comments? All right. So with that, let's play with some spectra. Okay. Do that. All right. Here are two emission spectra. What I want you to do is I want you to answer the question on the screen. Go ahead. All right. And here are our responses. This is good. This is good. This looks good. Okay, let's see. Now, for some reason, we do not have like that many UV, which but anyway, let's see what's going on here. Now, when you're given a question like this, the first thing you should do is mark your rainbow, at least the red and the violet. Okay, so we know 400 nanometers is violet. Okay, here's that's the crooked one, right? Here's my violet. Okay, and then here's my red. All right, so we got that down. Okay, and we see that we have shorter wavelength than 400 nanometers. Okay, so this must be what? Yeah, thank you, ultraviolet or UV. Okay, and then also we have longer wavelength than 700 nanometers, so red. Okay, that means this region must be what? Anybody? Yeah, it should be infrared. Okay, so in argon, we don't have much activity in the visible region. We don't have many light emitted in the visible region, but in the UV and the ion, there's a lot of light emitted by argon. But when it comes to helium, it emits light in the UV region, the visible region, and also some light in the IR region as well. Okay, so both, all three, UV, visible, and IR radiation are emitted by argon and helium. Okay, now, any questions so far about this? Anything? Yes, Novea. I met Lex this morning.
Funny.
Oh yeah,
Maybe?
please go.
Oh, okay. So for the graphs, it doesn't really matter like how tall the peaks
Yeah.
are. It's
Especially for emission, it doesn't. Yeah, no. It
okay.
doesn't
Like
matter.
if it's there, it's there.
Yeah, if it is there, it's there. Exactly. Any other questions? Do I have a question over there? No. No. Okay. So I saw that some of you picked microwave. All right. Remember, microwave does not appear until you go to 1 millimeter wavelength. Right. The longest wavelength here is 1200 nanometers. Right. Just for the sake of clarifying this, 1200 nanometers is, let's do this. Right. 1200 nanometers is, if you convert this to meters, we need to multiply by 10 to the power of minus 9, because that's how many meters you have in a nanometer. Okay. This is the same wavelength in meters now. But if you want to convert this to millimeters, we need to multiply this by 10 to the power of 3. Why? That's how many millimeters we have in a meter. So let me just do my favorite thing here. Okay, I like doing this. Nanometers cancel out, meters cancel out. You're going to get the answer in millimeters. Now you see that this value is around 12, it's not around, 1200 times 10 to the power of minus 6 meters, right? It is like 1.2 times 10 to the power of minus 3 meters, which is much less than a millimeter. Okay, so we are still in the IR region here. We haven't reached long enough wavelengths to get to microwaves, because to get to microwaves you need to reach 1 millimeter. That's where the microwaves start. Okay, so we are not there yet. All right. Do we have any questions, concerns, comments at the moment? Anything? Any questions, concerns, comments? All right. Now, with that, let's do this. I'm going to clear my doodling. All right. I'll reopen this question in case you revise your answers. That's okay. All right. Now, let's do two things. All right. So I'm going to give you two questions. One of them you're going to answer on top hat, the other one on your whiteboard. The first answer on your whiteboards. Okay. I want you to tell me what type of radiation is used to generate this spectrum. Okay. Number one on your whiteboards. And then second, make an observation. Okay. Answer the question on top hat. Go ahead. By the way, this units over here means micrometers. Okay. 1 micrometer is mu, Greek letter mu. 1 micrometer is 10 to the power of minus 6 meters. That's for whiteboard. It is IR. Okay. Now, how do we know this? Right, it's over here. All right, let me show you what I mean here. Okay, let me clear my doodling first. Okay, so we know, right, this is 10 to the power of minus 6 meters, right? So here's a straightforward way, I mean, based on the information given to you. So 10 to the power of minus 6 meters fall within this region over here. Okay, so you said that the wavelength is given in the electromagnetic spectrum down here. So 10 to the power of minus 6 meters fall within the IR region, and that tells you immediately that this should be IR radiation. Okay, that's the easiest thing to do. Okay, anyway, do we have any questions about that? Any questions, concerns, comments? Okay, so again, one more time. All right, you do not get microwave until you go to 1 millimeter. Okay, and then UV is somewhere else. It's in it's gonna have a much shorter wavelength than this. Okay, and visible as well. All right. Anyway, any questions, concerns, comments? Now I'll give you 30 more seconds to answer the question on the top part. Right? Does carbon dioxide absorb all the radiation or just certain wave? We go. Oh, look at that! Beautiful. All right. So most of us looking at the same thing, okay, we see that carbon dioxide only absorbs, okay, certain wavelengths of light, but not the others. All right. Now, here's the thing. Why? Not just carbon dioxide. If you think about any matter, it can be hydrogen, helium, or any atom or any molecule, okay? They absorb and emit only certain wavelengths of light, but not the others. Matter absorbs or emits only certain wavelengths of light because energy in matter is quantized. One more time. Matter only absorbs or emits certain wavelengths of light because energy in matter is quantized. Can somebody explain what is meant by that? Anybody? Who wants it? Okay, now it's like this. Okay. So what I mean by energy is quantized is, what I mean is we have certain energy levels in matter. Right? Only certain energy levels, but nothing in between. Still doesn't make sense. I know. That's okay. We'll get there. Okay. So what is meant by quantization of energy is energy in matter has certain levels of energy and nothing is in between. Okay. It's like this. Okay. If you take a ramp, say that you want to get to your roof. Okay. You use a ramp. Okay. If you use a ramp, your energy changes gradually from the ground to the roof. Okay. That is continuous change in energy. But if you use a ladder, okay, your energy changes in steps. Okay. You are in the ground, then you are in the next step, but you cannot be in between the step and the ground. It is not allowed. You can be either on the step or on the ground, not in between. Okay. You can be on that step or another step, but not in between the two steps. Okay. Energy in matter is like that. You have certain steps of energy in matter, and there's nothing in between. You cannot exist. Why only certain wavelengths are emitted and absorbed can only be explained by assuming that energy in matter is quantized. Without that, we cannot do that. We cannot explain it. Okay, that's the main thing. Any other questions, concerns, comments? And there are some other things like, photoelectric effect and stuff like that, which is going to be a bit beyond us. But yeah, anyway. So now what we're going to do now is, I know that we need to spend a little bit more time here to fully understand this. Okay. So what I'm going to do is I'm going to use the most simplest form of matter I can think of. What's the most simplest form of matter you can think of? An atom. What atom? Hydrogen atom, right? And that's the most abundant element as well in the universe. Okay. So we're going to use hydrogen atom as the example. Okay. And we're going to use the model called the Bohr model of the hydrogen atom. Okay. To explain the explain the spectra we have seen before. Okay. We're going to explain the spectra of hydrogen atom using the Bohr model of the hydrogen atom. Okay. That's going to be the goal. All right, let's do this. Now, this simulation is available to you as well. Because, scientists, whenever they are asked to explain something, they use a model, all right? This time around, to explain the spectra, we are going to use Bohr model of the hydrogen atom. All right, it looks something like this. Okay. Here's the Bohr model of the hydrogen atom. Okay. First of all, let's try to understand what is going on here. Okay. So in this model, there is a particle in the middle. What is that particle? Anybody? The particle, the blue particle in the middle is what? Anybody? Yeah, thank you. It's the nucleus. Okay, it's the nucleus. All right. And then there is another particle, okay? An obnoxious particle which is moving all the time. What is that particle? Yeah, that's the only electron that hydrogen has. Yeah, that's the electron. Okay, so right now we understand that much. Now, you see that this electron is in an orbit, the orbit closest to the nucleus. And there are other orbits as well. Okay, but right now, the electron is in the orbit closest to the nucleus. Now, when we have the electron closest, in the closest orbit to the nucleus, we call this state a special name. Anybody? What do we call this state? Harshini? Thank you. We call this the ground state of the atom. All right, let's make a note really quickly so that everybody will, get this jargon down now, okay? So let's go back to this. Here we go. Now, okay. When the electron is in the closest orbit to the nucleus, okay, we call that the ground state. This is the ground state. Okay, when the electron is in the closest orbit to the nucleus, we call it the ground state. Any questions so far? That's number one. We're just, getting this jargon out of our way. That's all we're doing now. Now, let's say that our electron is not in the closest one to the nucleus. Okay, if the electron is not in the closest orbit to the nucleus, okay, what do you call that state then? Anybody? Anybody? Yeah? We call it excited state. Yeah? So when the electron is anything other than the ground state, okay, in this case, let's define that. Okay. When the electron is in an orbit other than the closest to the nucleus. Okay, we call that an excited state. All right. Any questions, concerns, comments at the moment? Anything? Okay. All right. Now, let's get back to our simulation of the model. All right. Okay. Now you see that the electron is in the closest orbit to the ground state. And also, if you pay attention to this guy over here, this part over here, the electron is in n equals 1 state. Okay. So this orbit over here is the n equals 1. Okay. The next one is n equals 2. Okay. The next one is n equals 3. And this one is n equals 4. And it goes on, but we're going to limit, because this is a model, we're going to just limit this to 4 levels, but it can go up to infinity. Okay. Now, anyway, and then let me clear my doodling. You see that it tells you the energy in the n equals 1 is the lowest, then n equals 2, n equals 3, n equals 4, and it goes on like that. Okay. Right now, when the electron is, when the hydrogen atom is in the ground state, we have the electron in the lowest energy orbit. Okay, that's the idea here. All right. Now let me switch on the light source. Okay. I'm going to illuminate my hydrogen sample with 90 nanometer wavelength radiation. Let's see what's going to happen. Here we go. What happened? Show you something. Okay. Oh, okay. Here's 94. I decrease the energy now. Still nothing is happening. Okay. Let me increase it to 97. Oh, something happened. Right? Nothing happened at 90. Nothing happened at 94 or 96. But at 97 nanometers, what happened? Thank you. Yeah, electron jumped from n equals 1 to n equals 4, right? Yeah, it got excited. Yeah. So, okay. No, yeah, that's the way it is. Okay. It absorbs the 97 nanometer photon and got excited. Electron went from the ground state to an excited state. Okay. By absorbing the 97 nanometer photon. Okay. Now only 97, right? It didn't absorb anything else, only 97. All right, we'll talk about it a little bit more. But anyway, before that, now let's define absorption. Okay, this is what is happening during absorption process. When the electron absorbs a photon, the electron goes from the ground state to a high energy level. Okay, so let's make a note here. Okay, let's talk about what we observed in our notes. Okay, absorption. Okay. When the hydrogen atom absorbs light, the electron, I mean, we can use like fancy terms like promoted and things like that. We don't have to do that. Let's say the electron jumped from the ground state, that is the orbit closest to the nucleus, to an excited state. Okay. So in other words, if we make a small picture here of the Bohr model, here's our nucleus. Here's orbit 1, orbit 2, n equals 3, n equals 4. Okay. The electron went from the n equals 1 to n equals 4 in our case, or some other state. Okay, higher energy state, right? This is what is happening during light absorption, okay? In excited state. So if you want to, you can write that this is redundant, but that's okay. Within parentheses, we can write by absorbing a photon. Electron jump from the ground state to an excited state by absorbing a photon. Absorbing light. It's redundant though. Anyway, because we already mentioned absorption here. All right. Do we have any questions, concerns, comments at the moment? Anything? Only thing we did was we just made an observation. That's all we did here. Okay. All right. Let's do this though. Let's think about the energy. What are the two flavors of energy that we have talked about? The two flavors of energy that we have talked about are no, the energy. The energy. What are the two flavors of energy that we know? Kinetic energy, thank you. And the other one? Potential energy. All right, let's talk about the potential energy now. All right. Now, let's think about the potential energy. Let's call it E sub P for potential energy. Okay. Now, here's the question for you. Now, nucleus is positively charged. Electron is what charged? Thank you. Negatively charged. And what can you tell me about the interactions between them? Are they attractive or repulsive? Attractive, right? The electrons are attracted to the nucleus because they are oppositely charged. Now, where do we have the strongest attractive interactions? When the electron is in the ground state or when the electron is in an excited state? Everybody, the ground state. Why? When you are closer to each other, you're going to have the strongest interactions. Okay, we have when the electron is in the ground state, that's the closest the electron can be to the nucleus. That's where we have the strongest attractive interactions. Now, what's the mantra about the potential energy and the attractive interaction strength? Anybody who can remember the mantra? What's the mantra? Yes, sir. One more time.
As attractive interactions go up, potential energy goes down.
Thank you. The stronger the attractive interactions, the lower the potential energy. Right? So thank you. So you have the lowest potential energy when the electron is in the ground state. Now, upon absorption of light, what is going to happen to the potential energy now then? Potential energy must increase or decrease. It should increase because the electron is going away from the nucleus. When you are away from the nucleus, the attractive interactions are weaker, meaning it's going to have a higher potential energy than before. Okay, so let's make a note. During the absorption process, the potential energy increases. I'm going to use the up arrow here to indicate it's going up. It's increasing. Why? The attractive interactions between the electron and the nucleus are weakened when the electron goes to a high energy state, goes away from the nucleus. I didn't write that, but that's implied. All right. Do we have any questions, concerns, comments? Okay. During the absorption process, electron goes away from the nucleus to a high energy level. When that happens, the attractive interactions are weakened. Therefore, the potential energy increases. That's it. Okay. Now, let's do another thing. Obviously, we'll talk about the kinetic energy. But for that, I want you to pay attention to what is happening here. All right. One more time. Where do we have the electrons moving faster? Ground or excited? Can I see your whiteboards again? I see, thank you. I see ground. I see one excited, ground, excited, ground. Okay. Most of you are grounded. Thank you. Yeah. So if you make the observation though, look at it. All right. You see the electron is moving faster when the electron is in the ground state, when it is closest to the nucleus. It's just like the planets, right? When the planets are closer to the sun, they move faster than when the planets are far away from the sun. Okay, just like that, the electron is, I mean, same thing is happening with the electron as well. Anyway, so if that is the case, let's think about this. Let's complete our notes. All right. So the kinetic energy of the electrons must be greater in the ground state than in the excited state. Meaning, kinetic energy during the absorption process is increasing or decreasing? It's decreasing. Thank you. All right. So let's make that note. Okay. E sub K is for kinetic energy. By the way, if you are not used to this, this is kinetic energy. Kinetic energy, okay. Right, E sub K is kinetic energy. It's decreasing. Okay, so this is the observation. Okay, I'm gonna generalize it even more. Okay, when the electron, let's say electron in this case, electron has more space to move around, it slows down. Okay, decrease in the kinetic energy. When you go away from the nucleus, when the electron goes away from the nucleus, it has more space to move around. Okay, it just chills out. It just slow down. Okay, and then enjoy the ride. Okay. Anyway, do we have any questions, concerns, comments at the moment? Anything? One last thing here to finish our discussion about absorption, the total energy. Okay, so we see that the potential energy goes up during absorption. Okay, the kinetic energy goes down. Okay, on your whiteboards, what should happen to the total energy of the system? Go ahead. I say the total energy goes up. Okay, that's what I say. Okay, all right, meaning the increase of the potential energy is much greater than the decrease of the kinetic energy. All right, now I'm open. Okay, how many of you disagree with me? Okay, what law did I break here? Did I break a law? Energy cannot be, yeah, exactly. That's why I said energy must go up. Okay, yeah, I know. Energy can be created or destroyed. That's why I'm saying that energy must go up. Why? We had a photon absorbed by the hydrogen atom. Photon with some energy. What happened to that energy? You destroyed it, not me. So at this point, during the absorption process, let's do the same thing we had here. Here's N equals 4, N equals 3, N equals 2, N equals 1. Energy goes up in this direction. All right, during the absorption process, the electron goes from N equals 1 to, it can go to N equals 4, it can go to N equals 1 to N equals 3, we can go from N equals 1 to N equals 2, like that. Okay, by absorbing the photon energy or the photon. All right, so this recapitulates everything about absorption process. Okay, now anything about the emission then? Okay, you know what, before emission, so let's do this. Here we go. Here's a question for you on top hat, just to make sure everybody's on the same page. All right, here we go. Yep, this is it. Almost everybody agrees with this. Okay, all right. There are two. Anyway, that's okay. All right, now let's do the opposite now. Okay, let's think about the opposite. So what's the opposite of absorption? Thank you. The emission. All right. So what we want to do is we want to go through the same exercise with emission now. All right. So let's think about this. So I need to do this. Here we go. Let's think about the emission process. Emission. Okay. So what should happen in the emission process then? The electron should go from where to where? Come then again. Excited state to a lower energy state, right? So let's write that down. Okay. So electron moves, or let's say electron, yeah, let's say electron moves is better. We can say drop as well. That's okay. You know what? Let's use the word drop. Okay. The electron drops from a higher energy orbit to a lower energy orbit. Lower energy. I could have omitted writing orbit twice. Anyway, to a lower energy orbit. Okay. So what do I mean by this? One more time. Here's the Bohr model, our picture. Okay, n equals 1, n equals 2, n equals 3, n equals 4, and so forth. It goes on like that. Okay. So let's say that our electron is over here. Electron comes down from this this orbit to a lower energy orbit like that. That's an emission, because that's going to emit that excess energy as a light energy. Okay, it's going to emit a photon. Okay, so we can write here if you want to emitting a photon. Okay, the electron drops from a higher energy orbit to a lower energy orbit. Okay, emitting a photon or emitting light. Mean same thing. Okay, that is emission. And then during this process, what is going to happen to potential energy? Let's write potential energy now. No, let's be consistent. That's okay. E sub P for potential energy. All right. So during the emission process, what should happen to the potential energy? Should go up, down, or stay the same? Should go down. Thank you. The potential energy decreases. Okay. Why? Okay. The attractive interactions between the electron and the nucleus become stronger when the electron goes closer to the nucleus, right? Stronger. And that's why the potential energy decreases. Number one. What about the kinetic energy? Kinetic energy is increasing or decreasing? It's increasing. Okay. Kinetic energy increases. Okay. Why? Okay. When the electron has less space to move around, it moves faster. Okay. For that reason, kinetic energy increases. Okay. Now the total energy, E total. What can you tell me about the total energy? Yeah, the total energy must increase or decrease during emission. It should decrease. Why? Because we're emitting a photon. We're emitting light. We're emitting energy. we are decreasing energy. Therefore, we have to decrease the energy. Okay. The system energy must decrease. Okay. The total energy of the system decreases. Okay. Because the decrease in the potential energy is much more than the increase in the kinetic energy. Okay. Therefore, the total energy goes down. All right. One last thing I want to do. Right. So just for the completion, it's going to help with your reading assignment as well, which is due tomorrow, by the way. N equals 4, N equals 3, N equals 2, and N equals 1. Okay. So we have an infinite number of energy levels, but orbits, okay? But we are limited to this one because we cannot draw everything here, right? And then the energy goes up this way. Okay. Now let's say that we have an electron in N equals 4 over here. Okay. If that is the case, how many transitions are possible? All right. This N equals 4 electron can directly come down to N equals 1, emitting a photon. That's one transition. Okay. Or this electron can come down to N equals 2. That's transition 2. And then N equals 2 can come down to N equals 1. That is 3. Or this electron can come down from N equals 4 to N equals 3. That is fourth one. And then N equals 3 to N equals 2. That's going to be which one? Fifth one. And then is there another one possible? And then we can have another transition. An electron in N equals 3. Oh, that's give me a second. All right. And then N equals 3 can come down to N equals 1. That's going to be our sixth transition. So there are 6 transitions possible if